Assalamualaikum and a very good day to everyone. My name is Siti Fazila Nur Ain binti Sidi Omar, master's student of University Technology Mara UITM Shah Alam, and today I'll be presenting my research titled Computational Analysis and Optimization of Thermoelectric Performance, Investigating of Thermoelectric Material through Advanced Simulation Techniques. So for the research summary, the first one, we're gonna talk about the global population growth and rapid pace of industrialization is increasing, therefore facing energy supply depletions and environmental populations. Thermoelectric, which is being widely investigated, has a very clean energy conversion technology. It is a device that can convert from electrical energy to thermal energy and vice versa. However, thermoelectric has a problem of low efficiency and Za(T) low value. So Za(T) is the figure of merit. So the common thermoelectric material that been used is bismuth telluride, Bi2Te3. It has the best figure of merit nowadays, which is equal to 1. However, this material, the bismuth telluride, do not have a high resistance to high temperature, and it is high toxicity. So another alternative material that researcher is being looking at is the oxide perovskite. Has become more critical, can be used in high temperature. It is non-toxic and environmentally big nature. So this is some of the literature review that was done in this research, investigating on some of the material such as strengthened titanates, Ca2FeMoO5, CFMO, and a lot of other perovskite materials. From the literature review, we can find that the bismuth telluride is used widely in industry, but it's not high resistance in temperature. The second one is the perovskite can be seen to have a large potential for manufacturing because it's inexpensive, non-toxic, and readily available, and they have excellent thermal and chemical resilience at elevated temperature. From the research, the problem statements is bismuth telluride is the best present day as the best material for thermoelectric applications at low to medium temperature, but it's have poor thermal durability for high temperature and high toxicity and high material cost. And bismuth telluride can easily oxidize and vaporize in a high temperature applications. And the next problem is the low abundance of bismuth and tellurium in the earth crust is also a problem for manufacturer to find the material itself. In the research of thermoelectric, the period of time between discovering the material and the production is very long. Objective of this research is to analyze the electronics and thermoelectric property of oxide perovskite of two materials, strengthened titanate and CFMO, and the second objective is to express the ability and possibility of thermoelectric material in terms of figure of merits. The scope of this study is to use the COMSOL Multiphysics to stimulate two different thermoelectric material, which are CFMO and strengthened titanate, and this is to be compared with bismuth telluride. Next is the two different thermoelectric effect will be studied, which is the Peltier effect and the Seebeck effect, which is the two most popular effect in the thermoelectric, which the input data are different with each effect. Next, the research methodology. So the first is the thermoelectric material. So 3 thermoelectric was chosen: bismuth telluride, CFMO, and strengthened titanate, and the simulation are carried out in a steady state environment. All material are linear elastic, and all material are available in COMSOL Multiphysics. The conceptual geometry, there's two, which is first one is single leg and the second one is single thermocouple. For the meshing, the mesh is determined using a swept mesh approach, and the meshing pattern of the geometry was manually specified to increase the accuracy and saves calculation times. Next is the input data of the single leg in single thermocouple. So for the Peltier effect, we input data of current 0.7 A and 0 volt, initial temperature 273.15 Kelvin, and the Seebeck effect, we input data of hot and cold temperature. For the hot temperature of the Seebeck effect, we input 300 Kelvin, 400 Kelvin, and 400 Kelvin, and 0 volt, no current was input. For the single thermocouple, the same input that we use for the single leg. Data collection and analysis for the single leg Peltier effect. So we took temperature distributions and the electrical distribution result. You can see on the graph, strontium titanate and CFMO, the perovskite show a heating effect, which you can see the red and the blue graph show a heating effect, while the bismuth telluride show a cooling effect. Electrical distribution, both perovskite, the red and the blue, show a higher voltage compared to bismuth telluride. This is due to the electrical conductivity of the perovskite material, which is they have a higher. Second is the variation of the thermoelectric leg data collections. So we can see that the temperature difference of the thermoelectric for both material increase with increasing height. We increase 0 to 10, 0 to 10. And the temperature of CFMO produced higher than strontium titanate due to different thermal conductivity and the internal resistance of each material. For the electrical distribution, both have a linear increment, and as the height of the TE leg increases, we can see that the voltage output also increases. Next is the single leg Seebeck effect result. We can see that bismuth show a faster increment of temperature compared to both perovskite, and the electrical distribution strontium titanate produce a higher voltage. Next result is the single thermocouple Seebeck. We look at the temperature distributions and the power output. The single thermocouple is the two-leg thermocouple. So the temperature distribution, we can see that different material give different impact. Bismuth telluride has higher thermal conductivity, thus it shows smaller temperature gradients, resulting in lower percentage of thermally converted energy. You can see that the green is a bit higher than the rest of the perovskite. Next is the power output. Strontium titanate show higher power outputs compared to the other two material. The power also show increase with increasing temperature differences. This open up the possibility using the material strontium titanate in higher temperature TEG derivatives. Next is the status of my research, which is data collection and analysis. Most of the data collection is 100% ready, except single thermocouple Peltier effects, which is only 50% left. List of publication: three publication, 2 accepted and published, 1 is accepted with minor corrections. The status of thesis writings. So 5 chapter: introduction, literature review, research methodology, result and discussion and conclusion. Research methodology is 100% ready. Introduction, literature review, conclusion 90%, result and discussion 70% because of the single thermocouple Peltier effect is not ready yet. Future work, completion of thesis, and LOI from submissions. Thank you, that's all for today.